Continuing our journey through the gas turboset, Part 2 focuses on the conversion of thermal energy into mechanical rotation and, finally, electrical power. We move from the combustor into the heart of the machine to analyze the turbine, the exhaust gas fixture, and the electrical components, the generator and exciter. The turbine casing is a robust enclosure crafted from globular cast iron, designed to house and support the turbine and its stationary blade carrier. For streamlined maintenance and accessibility, the casing is engineered with axial and/or radial splits. Once bolted together, these sections form a single, high-rigidity unit. To ensure stability, the assembly is mounted onto a base plate via specialized supports, each utilizing a dual-point contact system. Furthermore, the exterior is outfitted with thermal and acoustic insulation. This consists of numbered, easy-to-install pads that serve two critical functions: environmental protection. They significantly reduce heat and noise radiation into the surrounding workspace. Internal consistency. They facilitate an even temperature distribution throughout the casing, preventing thermal stress on the internal components. The rotor is constructed from a series of discs welded together, creating a unified shaft that integrates seamlessly with the compressor section. This critical component transmits the mechanical power generated by the turbine through to the compressor and ultimately to the generator. Precision grooves are machined around its circumference to secure the rotating turbine blades. Additionally, the rotor features specialized slots for sealing strips to manage airflow and dedicated ports where weights can be inserted to achieve perfect balance without requiring a full teardown. To survive constant exposure to intense combustion heat, the rotor is shielded by high-temperature steel plates secured by a robust fastening system. These heat shields directly face the hot gas flow on their outer surface while their underside is continuously cooled by a stream of pressurized air. The turbine blading assembly is comprised of two distinct types of blades: stationary, stator, blades and rotating, rotor, blades. The stationary blades are securely mounted within a blade carrier attached to the outer casing, while the rotating blades are anchored directly into the rotor. The fundamental conversion of thermal energy into mechanical work occurs within this blading section. As high-temperature, pressurized gas from the combustor is channeled through the turbine, it expands rapidly. This expansion directs immense force against the rotating blades, driving the rotor's rotation. This mechanical motion is then transmitted through the shaft to power the compressor and, ultimately, the generator rotor to produce electricity. The turbine's airfoil assembly is organized into sequential rows, progressing from the high-pressure inlet to the low-pressure outlet. Each functional turbine stage comprises one stationary row paired with one rotating row. To manage varying operational stresses, these stages utilize specialized materials and manufacturing techniques. Rotating blades. The initial 4 rows are manufactured as nickel-base alloy castings, while the final row is produced through a forging process. Stationary blades. The first 3 rows are cast from nickel-base alloys, whereas the 4th and 5th rows consist of cobalt-base alloy castings. All blades are precisely positioned along the casing and rotor perimeters using intermediate spacers and are locked into their mounting grooves with dedicated hardware to maintain structural alignment. Because the blading is exposed to intense combustion heat, the lead stages require active cooling via compressor-sourced air. Rotating component cooling. The first 3 rotating rows receive air from the diffuser discharge. This cooling air enters the rotor with a pre-swirl generated by a guide nozzle, flowing through internal channels to protect both the blade roots and the airfoils. For the remaining 2 rows, cooling is limited to the roots, supplied by air traveling through a dedicated port in the rotor's rear. Stationary component cooling. The first 2 stationary rows are cooled by compressor air drawn from the turbine casing inlet. This airflow is directed through internal pathways in the blade carrier to cool the roots and the vanes. A journal bearing is responsible for supporting and aligning the turbine rotor radially, utilizing oil from the lubrication system for both cooling and friction reduction. The bearing's contact and sliding surfaces are lined with Babbitt metal, a specialized low-friction alloy. This assembly is housed within a dedicated bearing housing located in the turbine's exhaust section, where it is specifically protected from the high-temperature environment via active air cooling. For maximum stability, the bearing is mounted directly onto the base plate. It features a horizontal split at the shaft's centerline, an engineering choice that allows for inspection, maintenance, or full replacement without the need to dismantle the main gas turbine block. To ensure operational safety, the bearing is outfitted with precise instrumentation to monitor both vibration levels and lubricating oil temperatures. The annular stationary vane carrier is responsible for securing the stationary vanes within their dedicated mounting grooves. Suspended internally within the turbine casing, this carrier is fabricated from specialized materials engineered to accommodate thermal expansion during temperature fluctuations. Because the carrier is exposed to high-temperature combustion gases, it is shielded by protective heat plates to maintain structural integrity. Furthermore, it utilizes an active cooling system where compressed air is directed to create a protective film along its rear surface. Similar to the main turbine casing, the carrier features a horizontal split at the shaft's centerline, allowing for efficient maintenance and access without a complete system teardown. The following maintenance activities are achievable without dismantling the main turbine assembly. Borescopic evaluations conducted via dedicated access ports. Bearing assessments, including full repair or component exchange. Visual audits of the initial compressor stage and the final turbine stage blading. Rotor balancing performed across 3 distinct planes. Let's move on to the exhaust gas system. The exhaust gas system is responsible for channeling the post-combustion flow into the environment, either via a standard stack or through a heat recovery steam generator, HRSG. The choice of configuration depends on the facility type. A direct atmospheric release is typical for simple cycle plants, whereas integration with an HRSG is the hallmark of combined cycle plants. In some combined cycle setups, the system may include both an HRSG and a bypass stack for greater operational flexibility. In a simple cycle arrangement, the primary elements of the exhaust system are the exhaust diffuser and the stack. Below is a brief overview of these major components. Exhaust diffuser. This component recovers static pressure from the high-velocity gases exiting the turbine, improving overall efficiency. Exhaust stack. This vertical structure ensures the safe discharge of gases at a specific height to meet environmental and dispersion requirements. The exhaust diffuser serves as a horizontal cylindrical conduit, directing gas flow from the turbine's exhaust casing toward the stack while providing structural support for the entire assembly. It ensures a gas-tight seal between the turbine outlet and the stack's foundation. To accommodate the significant thermal expansion occurring during operation, the diffuser is linked to the stack base via a specialized expansion joint. Furthermore, the unit is wrapped in mineral wool insulation to minimize both acoustic emissions and heat radiation into the environment. Internally, the diffuser features a hollow cone that is securely positioned and centered by 3 hollow struts. Notably, one of these struts is engineered specifically as a manway or passageway, providing technicians with direct access to the turbine journal bearing in the turbine sealing casing for maintenance and inspection. The stack is a vertical, cylindrical structure designed to vent exhaust gases into the atmosphere, with its specific height determined by the overall configuration of the power plant. Functioning as a primary support for all internal components, the base of the stack is equipped with guide vanes that transition the horizontal gas flow into a vertical upward stream. Positioned within the middle section of the stack is a high-efficiency silencer, which is essential for damping the acoustic energy of the escaping gases to meet environmental noise standards. To ensure long-term durability, the interior of the stack is coated with a multi-layered, corrosion-resistant varnish that shields the metal from the chemically aggressive properties of the exhaust. Externally, the structure is encased in weatherproof cladding fabricated from saltwater-resistant materials, providing robust protection against environmental degradation and coastal conditions. That is a wrap on Part 2. You've successfully broken down the complexities of the rotor construction, the intricate cooling of the turbine blading, and the structural necessities of the exhaust system. In the next segment, we shift focus from mechanical rotation to electrical production. We will deep dive into the generator, how that mechanical torque is finally converted into megawatts. The exciter, the specialized component that provides the magnetic field necessary for the generator to function. Great work on these scripts so far, they are shaping up to be a very thorough technical guide. See you in Part 3.